Good morning, all of you. Today we are going to talk about our design project. Our design project is integrating soil water balance modeling for sustainable water management in cascade system. First of all, I want to thank some people who helped to our project work. First, our external supervisor, manager, Mrs. NCW Kunasekara from National Water Supply and Drainage Board. Then, our internal supervisor, Professor AMKB Abhesinkar from the Department of Earth Resources Engineering. And we are sincerely thanking to our HOD, Dr. LPS Rohit. Then I am thanking to Meteorology Department for providing essential data for this project work. And lastly, I am thanking to our team members for their work and helpful to our design project work. Today, we are doing our presentation through these headings. First, introduction, then objectives, then input data, next, data conversion, results, applications of model, future improvement, lastly, conclusion. Now, we will move to next slide. Why we are doing this project? Yeah, in Sri Lanka there are so many cascade systems are there, and they are doing very big role in irrigation, groundwater recharge, and livelihood support in the dry zone as well. But because of some reasons, these systems are facing rising challenges. But in this big situation, there are no any scientific tool to quantify groundwater recharge variations. This is the very big problem in Sri Lanka. So, as a earth resources engineers, we decided to develop an integrated soil water balance model in Bandarakumbuk Wave Cascade under the Anuradhapura district. We chose this cascade because this is under the Anuradhapura district. Now we will move to next slide. These are the objectives of our project. The first one is develop a GIS based soil water balance model using our GIS Pro software. But we can use QGIS software and ArcMap as well. But in our project, we use ArcGIS Pro software. The second one is estimate spatial and temporal variations in groundwater recharge. The next one is analyze the impact of different land use types. The examples paddy, forest land, urban land, wetland, scrubland, and etc. The last one is propose recommendations for sustainable groundwater management and planning. These are the input data of our project. The first one is precipitation data. This one calculate from rainfall data. The next one is temperature data. Next, land use map, soil type map, topography map. The last one is soil water content. Now we will see the methodology part that we use to create the maps. The first one is land use map. In here, first of all, we import the cascade boundary save file into ArcGIS Pro. After that, we used satellite imagery as base map tool to create polygons inside of our study area. In here, we found so many land uses. Those are paddy land, forest land, scrubland, barren land, wetland, and grassland as well. After this step, we assign land codes to the land users according to the lookup table. After these all steps, we applied symbology to generate the final land use map. This is our land use map. The next one, to create the soil type map, we used land use map as our primary map. First of all, we change the type of our map to raster by using polygon to raster tool. After this, we use reclassify tool to assign soil type map according to their soil type categories. In here, soil type categories are depend on infiltration rate. In our map creation, we use four main soil types. This is the soil type map that we created. Next, we will move to soil water content map. This is the soil water content map that we created. Here, the method we used is like before. Here we categorize the water content map according to the water content capacity, like clay, sandy, silky clay, loamy sand, sandy loam, like this. This is the topography map. In here, we import the Sri Lankan DEM data. After that, we clip the DEM data according to the study area to isolate it. After that, we use fill tool to remove things and those things. In end of this work, we generate the D8 flow direction map using the direction. After the data preparation work, we change all data into correct format to run the code. In here, all spatial raster layers change into ASCII format and the climate data was formatted into text file format. After run the code in the command prompt, we took these results. According to these results, we can calculate the spatial and temporal variation in the groundwater recharge of various land uses. It's important for water quantity variations, water quantity protection, groundwater flow modeling, and understanding the effect of development in urban, industrial, agricultural land uses. These are the bar chart and graphs that we took from the result. We can take the details from these charts and maps and graphs according to our usage. Now we will see how we can improve the model. The first one is use real-time rainfall data and temperature data. By using current year data, we can get more accurate recharge estimates. The second one is create mobile dashboard. By using this method, in future, the farmers and the water managers can easily see the results. The third one is simulate climate changes. By this, we can predict groundwater availability in the future. The next one is expand the model to the whole dry zone. By using this method, we can take more accurate recharge estimates and the regional water management planning can do. The last one is combine with groundwater flow models. By this, we can better understand water movement in the underground. We can use ModFlow software to this work. We will see the conclusion part of our presentation. First, we developed a GIS based soil water balance model and it shows how groundwater recharge change through the space and the time. Then it helps plan and manage water resources sustainability. Next, it can guide policymakers and support development decisions. In our design project, some limitations also there. The first one is data gaps and assumption. In here, some climate data and the soil properties were sourced from the secondary literature instead of the field measurement, which may affect the accuracy. The next one is each land use category was assigned a single recharge value. although actual recharge may vary within the same classes due to the farming practices or vegetation density. The next one is the DEM and raster resolution may not perfectly capture microtopography features affecting the runoff estimation. Next, human impact such as pumping from the wells or irrigation withdrawals were not factored into the recharge balance. The last one is the model was developed using the non-license, it been cracked version of the RGA's Pro software, which restrict access to the advanced geoprocessing tool and automation features. Thank you for listening to our presentation. We hope our project contribute to future water management efforts.